Mixtures of gases and partial pressures. So last little bit for talking about one more law and a few other equations about this chapter for the simple gas laws and talking about gases ideally until the second part of this chapter we talk about real gases and how the equations change a little bit. So basically, many gas samples are actually not pure. There are always little mixtures of other gas components that make that gas what it is. Molecules in an ideal gas, they don't come together and form something new. They don't interact. They are in the same container and constantly colliding with the surfaces of the container, but not colliding with each other to make something new. Thus, each of the components in an ideal gas mixture, they act independently, so they give off their own pressure to make this pressure of the gas overall. A great example of that would be air. So the air contains nitrogen molecules of around 78% of its pressure, and it's independent of the oxygen that's in air and the argon that's in air. The pressures that come from individual components in a gas mixtures are all called partial pressures. So for example, air, the big pressure of air, the atmospheric pressure that we see, is composed of the partial pressure of nitrogen, oxygen, and argon that it's made up of. That law is called the Dalton's partial pressure, and it's the total pressure of a substance is equal to the partial pressure of however many components it has. Here I have A, B, and C. It could continue, or it could be shorter than that. It just depends on how many components you actually have in the mixture. So a component of a mixture's partial pressure can be determined using the ideal gas law equation. So you can specifically, we know that the ideal gas law equation is equal to PV nRT. And I can say that this is my PA and my moles of A that are contributing for me to get my partial pressure of just my substance A in the mixture. However, it can also be solved another way depending on the information you're given. The partial pressure, P sub A, again, P sub B, whatever mixture you're looking for, of a substance can be calculated using mole ratio and a total pressure of the mixture. So because we know that this is a ratio, if I multiply the ratio to the overall pressure of my solution, I can get how much that one substance contributed in pressure units. Well, how do I find mole ratio? Since it's a mole ratio, it will be the amount of moles of that particular substance divided by the moles total. So you can apply these equations different ways depending on what you're looking for. If you are given all the information for a substance, that's total amount, you can find the pressure total using ideal gas law. And if you have the moles of the substances or the mass or other information, applying different things we've learned thus far, you can find mole ratio. Or you can even apply ideal gas to find the partial pressure of a substance and just look for different things in this equation that you need to solve for, applying this, etc. I'm mentioning these things just because it's not sometimes as black and white. It's kind of puzzling the different things together for a bigger picture. And with that said, let's practice. But before we do that, actually, I want to go over one more thing. So what I want to say is where this comes from, because you know that a mole fraction is the number of moles of component A and the total moles of a sample. And because we can apply this, let's just say that if I rearranged this to have PA is equal to NA RT over VA, or V, right? Well, RT and V, the volume, the temperature, and the gas constant do not change of your total pressure and your pressure component. It is the number of particles and the pressure that are changing. So if you wanted to know the ratio, P over PT, it would be the NA RT over V over N total RT over V, which then would give us just that the pressure of a substance over the total pressure is equal to the moles of that particle over the total moles, which is therefore the mole fraction. Just showing you a little bit of the derivation where partial pressure and mole fraction are coming from. A driver breathes a heliox mixture with an oxygen mole fraction of 0.050. Okay, I'm going to stop there. So I have oxygen mole fraction of 0.050. What must be the total pressure? So I'm looking for PT, I don't know this. For the partial pressure of oxygen to be 0.21. So I'm given my partial pressure, I'm given my mole fraction, I want my total pressure. Well, I know that partial pressure of a substance relates to the mole fraction of that substance times the total pressure. So if I'm looking for my total pressure, I would rearrange my equation to look for the ratio of the partial pressure and mole fraction and then plug everything in. Note how the mole fraction is unitless because it's moles divided by moles, which would cancel out, and you would be left with just atmospheres, and your answer would be 4.2 atmospheres total pressure. Alrighty, last little bit for the partial pressure is also talking about vapor pressure. And vapor is steam, right? So this happens when there's bubbling going on. So look at this little diagram here. Know how you have this test tube where you have this desired sample, right? You have zinc. So what you did is you placed zinc into a test tube that has hydrochloric acid in it. And what that does is the zinc will react with the chlorine to form an aqueous substance and produce hydrogen gas. So these bubbles that you see are hydrogen gas. And so through this apparatus, what happens is through our manometer, the U-shaped tube, the hydrogen gas particles are collected. And then through an inverted beaker, you can actually find the number of gas particles that can be obtained. So when the desired product of a chemical is a gas, the gas can often be collected by the displacement of water. As the hydrogen gas forms in this reaction, it bubbles through the water and gathers in the collection of the flask. So you can see that we have all of these water molecules that are being gathered, and that the atmospheric pressure holds the water level to a certain spot because it's pushing down. So based off of this difference between where the water level started and where it's ending, we can calculate the displacement of the molecules. The hydrogen gas collected in this way is not pure because there is water, so you have to account for the water molecules in it. It is mixed with the water vapor because some of the water molecules evaporate and combine with the hydrogen molecules. So it's not just water, it's not pure hydrogen. Some of them do mix sometimes. The partial pressure of water in the mixture depends on the temperature, which is called its vapor pressure. And just to know that since this has to do with bubbling and a reaction and vapor because of the steam of the water, it increases with increasing temperatures because higher temperatures causes more water molecules to evaporate. So then we can collect the hydrogen over water by saying, all right, well, my pressure total is equal to my pressure hydrogen plus my partial pressure of water. Well, my partial pressure of water is known. There's a table with different partial pressures of water since it's always the vapor pressure, the amount of gas particles collected in its vapor at certain temperatures. And the total pressure you can calculate. So therefore, if you know these two, you can then calculate the partial pressure of hydrogen by subtracting the total pressure minus the vapor pressure of water. So in this way, we can determine the exact pressure of a hydrogen mixture from a desired reaction that's happening. Putting this all into a reaction. So all of the different rules and concepts we've learned so far can apply to gases as well. And the best way, rather than just writing out a bunch of definitions and steps, is to learn through a problem. So methanol can be synthesized by reacting carbon monoxide and hydrogen gas. What volume in liters of hydrogen gas at a temperature of 355 Kelvin and a pressure of 730 millimeter mercury is needed to synthesize 35.7 grams of methanol? So let's just write here what I'm given. So I'm going to write it up here. Given what volume of hydrogen gas at a temperature, so I have a temperature of 355 Kelvin, a pressure of 730 millimeter mercury, and 35.7 grams. So I want volume, but now exactly of what? So what volume of hydrogen gas? So I want volume of H2 at a temperature of 355 Kelvin and a pressure of 730. So these are also of hydrogen gas, but the mass is for methanol. So immediately I notice that I have information of one substance and of another, and I want to know the volume of hydrogen gas. Well, if I'm given temperature and pressure and I want volume, I would think, well, I know ideal gas law. And I know that I can find my volume based off of the moles, the gas constant, the temperature, and the pressure. But what am I missing here? What do I not have yet? I don't have my moles. This is unknown. So I first have to solve for my moles of hydrogen gas. Well, I'm still given a piece of information. I'm given the mass of methanol, but I need moles of H2. Can I get there? Yep, because I know that I can go to moles of methanol using molar mass. And from there, I can go to moles of H2 using stoichiometry. So if I need to use stoichiometry mole ratio, what should I do? I have to write my equation. So it tells you that methanol is synthesized from carbon monoxide and hydrogen gas. So the reaction of synthesis is A and B coming together to form AB. So that means we have carbon monoxide plus H2 to make methanol. Now take a moment to try and balance this equation. We need 2 here. And now I have enough to start. So 35.7 grams of methanol. Well, I already kind of wrote myself a plan here. I have to convert to moles using molar mass. And then I have to use my ratio. So 2 moles H2 over 1 mole methanol. And that gives me 2.22 moles H2. Awesome. And now I can go to my ideal gas because I have all my other information. Making sure you convert the appropriate units. So I already did it. We already know that we have Kelvin. And then we just need to convert the pressure to atmospheres because that's our gas constant is in atmospheres. You plug everything in and you will get 66.9 liters. So using a couple different concepts to find your overall goal, knowing kind of making yourself a plan, like what do you have, but what do those represent? Do they all represent one substance? Do they represent multiple substances? What do you need? How can you get there? Couple little self-check problems. How many liters of oxygen are required to form 10.5 grams of water at STP? So what do I know at STP? I know that I have a pressure of 1 atmosphere and I have a temperature of 273.15 Kelvin, and I want liters, so I want volume. And I'm also given my mass of 10.5 grams. Well, I know I can use my ideal gas. However, I want to know oxygen, and I'm given the mass of water. So I'm going to need to write myself an equation. And then I can do the same exact process that I just did. So since I'm given all this information of O2, I know that I can use PV is equal to nRT, V is equal to nRT over P to get my volume. But I need moles O2. I don't have that yet. Since I'm given my mass of water, I can use all the different applications I already know, molar mass and mole ratio, to get that amount. So then I can just plug everything in. And then if you plug everything in, you would get 6.52 liters. And you're done. In the decomposition reaction of silver oxide, 4.58 liters oxygen forms a pressure of 754 millimeter mercury and 308 Kelvin. How many grams of silver oxide is decomposed? So we have a volume of 4.58 liters of silver oxide, so Ag2O. And, in the decomposition of silver oxide, 4.58 liters of oxygen forms, so we just have O2. A pressure of 754 and 308 Kelvin, so we have P is 754. And then temperature is 308 Kelvin. How many grams of silver oxide do we have? Okay, so I want to know grams of silver oxide. So let me write my equation first. Decomposition reaction. So that means Ag2O is decomposing to silver and oxygen. And to balance, we would need a two here and then a 4 here. Awesome. So if I want the mass of this, I can convert, since I have all this information from oxygen, using my mole ratio. Now I'm going to let you try this one on your own, knowing that you have pressure, volume, and temperature, and since you know ideal gas, if you have pressure, volume, and temperature, you can solve for the moles and kind of work backwards to get the mass of silver oxide. When hydrochloric acid is poured over potassium sulfide, 42.9 milliliters of hydrogen sulfide gas is produced at a pressure of 752 torr and 25.8 degrees Celsius. Write an equation for the gas evolution and determine how much potassium sulfide is reacted. So this is going to be a little bit of your own practice problem here. There is a gas evolution reaction, so it gives you a good little background of what to write for that reaction and to balance it, and then working backwards to solve for the grams that you want. And that's it for today.